Part A, 3a, is after dy by dx. So we're looking to differentiate the function. So differentiation is bring down the power, take one off the power. So we're going to have bring down the power 6 over 2 x. Take 1 off a half, we get to the minus a half. Differentiating x just goes to 1, and differentiating a constant just disappears. So we find out that dy by dx is equal to 3x to the power of minus a half minus 1. And if we're going to be doing any substitution into this, it's worth already thinking about this as the minus in front of the half there means that it's 3 over x to the half minus 1. And then x to the half, well, that is 3 over root x to the minus 1. And I think it's always worth keeping in mind what the function's actually going to look like, particularly in Core 2, when we might be substituting in to that function. And from here, we then move into B. Hence, so using what we've just found, we're being asked to find the y-coordinate of the maximum point M. So to be a maximum point, it is a stationary point. We know it's a maximum because we can see it is on there. So what we are doing is we're going to put dy by dx equal to 0, because when it equals 0, that gives us our maximum value. So we've got 3 over root x subtract 1 equals 0. And I'm just going to scroll down to give myself a bit more room for this. So rearranging this, then it's 3 over root x equals 1. And then multiplying both sides by root x, I get 3 equals the square root of x. So then if I want the x value, I need to square both sides. So x equals 3 squared, so x equals 9. So that's the x value of the point M. So the x value here is 9. The question asks for the y coordinate. So what is the corresponding y value? Now, in order to find that, we need to substitute the x coordinate into the equation for y. So y equals 6 lots of x to the half minus x minus 3. So y equals 6 lots of 9 to the half minus 9 minus 3. Now, this is Core 2, you've got your calculator available to you, so it's worth using because it saves any little slips or anything like that. So we're just going to put all of this straight into the calculator, and we get the y coordinate is equal to 6. So what we're after here, hence find the y coordinate of the maximum point of M, the y coordinate is 6. Okay. Now for part C, find an equation to the normal to the curve at the point 4, 5. So I'm just going to remove my workings for B, but quite useful are going to be what I've just found for the differential. So I'll leave the dy by dx and what that equals just up there for a moment. So if we just scroll back up, we're looking for the normal to the curve at 4, 5. So 4, 5 is probably somewhere about here. Okay, the first line I'm going to draw in, this is the tangent to the curve. We're not interested in that. And then the normal to the curve is this dotted line, if you like, that I'm drawing in here. So the dotted line is the normal. So what do I need to know? I need to know the gradient and I need to know a point, because if I'm doing part C, I want to be using my formula y minus y1 equals mx minus x1, because that's the way in which I find the equation of a line. So I know my y1 and my x1, they are the point P. I just need to know m, the gradient of the normal. So the gradient of the normal, well, that is the negative reciprocal of the gradient of the tangent. So the gradient of the tangent is going to be found, so that's what I want to know. I want to know the gradient of the normal. To get there, I need to know the gradient of the tangent. So that can be found by substituting in x is 4 into dy by dx. So 3 over the square root of 4 minus 1. So this is going to be giving me the gradient of the tangent. So again, core 2, so it's worth just making sure I get everything right using my calculator as much as I possibly can. And even if we can see what's going to happen here. So we end up with a half. So the gradient of the tangent is a half. So therefore, the gradient of the normal is the negative reciprocal of that. So flip it over and change the sign. So the gradient of the normal is minus 2. So then to put this together, the equation of the line is y minus 5, because that's the y coordinate of p, equals minus 2 x minus 4, because the x1 is the x coordinate of p. Now you need to stop there, because if you rearrange this, expand it, you're just wasting time. You've got your 3 marks there. You might as well finish the question and move on to part D. Okay, so on to part D. Okay, so in part D then, we are being told that it's given that the normal to the curve is translated by a vector k naught, passes through the point M. Find the value of the constant k. So what this is telling us is that this line, this dotted line that I've called the normal, if that gets moved, I'm just going to change the colour here, that's going to get moved only in the x direction. So it only gets moved across, it doesn't get moved up or down, to the point where it's passing through M. So we get this newly translated version of the curve. So that's over here. Okay, now our mark scheme gives us 3 possible methods to solve this question. So it's quite a tricky one that you probably haven't approached before. So if we just think about, that's what we're going to have to do. We're going to have to think about the fact there's been this movement k that's taken us across some way, not up or down at all, and we're trying to find out what that distance is, how much we've moved that curve across. So there are different methods. You could consider this point here and consider the point here. So the 2y values, where does it move to? And that would give you enough information. That's not the method I'm going to use. The method I'm going to use is to think about taking the equation that we've just found. So the equation of the line. So we've just found that it's y minus 5 equals minus 2 x minus 4. Okay, and we are trying to move this, so this has been translated k0 so that it passes through M, which in the previous parts of the question we found out the coordinates to M, which were 9 in the x direction and 6 in the y direction. So if I'm changing my x value by k here, my new equation is going to have the x value changed. So the x value, and that's going to be subtracted k. It's happening to the x, it's happening inside the function, it's taken away, so it's the opposite to what we expect, and then we've got our minus 4 there. So that's effectively our equation of our translated curve, i.e. looking at the picture, this is the red curve, the red line, sorry, it's not a curve, the red line. If we then put in our coordinates for M, because if we just go back up to the picture quickly, the red line passes through M, okay? So if we can put this in together, this will solve for this problem. So let's put in x and y. So 6 minus 5 equals minus 2. X is 9 minus k minus 4. So now we've got an equation with just one unknown. So if we solve this equation, 1 equals minus 2. 9 take away 4 is 5 minus k. Okay, and then we're just going to keep manipulating this. So if I expand the bracket, I think it's going to be a bit easier to do it this way, plus 2k. So add 10 to both sides. So 11 equals 2k, and k is equal to 5.5. And that's our correct solution. So what we've done, just to recap, because as I say, this is not something, it's not a standard sort of question. We've decided that we're moving our curve just in the x direction. So we are changing our given, or the equation that we've found, we are changing that to move it k units in the x direction. So what does that look like? That looks like our old equation, but instead of having x, it's got x minus k there. because we're moving it k units in the x direction. From there, we then substitute in the fact that this new line, this is our red line, goes through the point 9, 6. So it goes through 9 and 6, substitute that in, rearrange through, and we can find out the value of k. And that is then the question completed.